Welcome to Mrs. Z's Chemistry. This is 13.4, Part 2, where we're going to do some practice problems with molar solubility and solubility product constants. Here's a sample problem. The solubility product constant, which is KSP, for nickel 2 carbonate is 1.3 times 10 to the negative 7 at 25 degrees Celsius. The temperature is usually always included whenever a K value is expressed, and that's because the K is dependent on temperature. If that temperature were changed to, say, 35 degrees Celsius, this K value would be a little bit different. However, the temperature, the actual number, the numerical value of the temperature is not used to calculate K, so you can ignore it when it comes to the math. A. Write the balanced chemical equation. This means write the balanced chemical dissociation reaction for nickel 2 carbonate. First, we need to use our naming rules to figure out what nickel 2 carbonate is. Nickel is a transition metal. We don't know what charge it is just by looking at the periodic table. But if you look at the back of your periodic table on the common polyatomic ion list, you can see that carbonate is CO3 with a 2- charge. The Roman numeral on nickel in the name tells you that nickel has a 2+ charge. Therefore, 1 nickel and 1 carbonate gets us nickel carbonate, and that is neutral. These reactions always have one ionic compound, or salt, as a solid on the reactant side, the left-hand side. Write a double arrow. The dissociation reaction is what nickel carbonate, or the ionic solid, breaks apart into. It always breaks apart into a positive cation, usually always the metal, and a negative anion, usually always the nonmetal or the polyatomic ion. So in this case, we have nickel. You must always include the charges. This is an ion, very specifically a charged particle. Nickel is a drastically different component when it is charged versus when it is neutral. When it's neutral, we can assume it is solid. It is a hunk of metal that you could hold in your bare hand. A charged nickel ion is dissolved in water. It is an individual teensy-weensy little particle that you cannot hold in your hand. And then carbonate. Same thing. You must include charges. These are aqueous because that is what dissociation means. One solid turns into aqueous, two aqueous ion compounds. That is your dissociation reaction. Now B, write the equilibrium expression. This is products over reactants, no solids, no liquids. Coefficients turn into exponents, and there are no values plugged in. So yes, we have the value of K right here, but it's not asking for that. It's asking for the expression. So you write K, because we know that this is a KSP from here. You can also use the little subscripts of SP. The products are on the right-hand side of the arrow. That is nickel. Charges must be included on the inside of the brackets. Nickel does not have a coefficient, so leave that without an exponent. Carbonate, with its charge on the inside of the brackets, there is no charge, and that is how we leave this, because the only reactant that would be in the denominator is a solid. You could, I suppose, theoretically, use it 1 as a placeholder, but you also don't have to. Find the molar solubility of the solution. Molar solubility is X from a Rice table, if we were to write out a Rice table. So let's go ahead and do that. We have our reaction. The nickel carbonate solid on the left-hand side is a solid, so we're not going to do anything with it in the Rice table. It's not going to be plugged into our expression, so we don't care what the value is. Whatever solid amount you had on this side over here, you have 0 of the products, because you can imagine we have our solid crystalline structure that we've weighed out on a scale, and before you drop it in water, we have 0 nickel ions and 0 carbonate ions. Some amount of nickel ions and carbonate ions will dissolve or dissociate, and that value is represented by X. So you can see that you cannot get a nickel without also getting a carbonate. You cannot get a carbonate without also getting a nickel. These two values are equal to each other, which is why they can both be represented by X. If you plug in X for nickel and X for carbonate, it looks like we have KSP equals X times X, which could be simplified as KSP equals X squared. The KSP value is given at the very beginning of the problem right here, so plug that in for KSP. And this actually should be in X. X is equal to the nickel carbonate, or the nickel ion, which is also equal to the carbonate ion. When you take the square root of your KSP, we get this value. Pause to see if you can digest this information. Here's another example. The solubility product constant, KSP, for lead to iodide is 7.39 times 10 to the negative 9. A, write the balanced chemical equation. Pause to see if you can do this before seeing the answer. From our naming rules, we know that lead is a 2 plus charge because of the Roman numeral. So that is a lead 2 plus. Iodine is where iodide comes from. Whenever it's an ion, you change the ending to "ide," which is why iodine is now iodide. Iodine always has a -1 charge. Therefore, we must have two iodines. See, -1 equals, or can neutralize out our positive charge from the lead. So we have two iodines and one lead to make a neutral compound of lead iodide. This is a solid. It dissociates or breaks apart into the one positive lead cation and the two separate individual iodide ions. I know that iodine, as well as a handful of other elements, are listed as diatomic on the back of your periodic table. That is for when those elements are in elemental form by themselves. So if we were to write this, that is automatically assumed to be gaseous or liquid, whatever it is in at room temperature, and that's an elemental form. But that's not what we have. We are creating iodine ions. They're charged. They each have an extra electron, and they are separate away from each other. They are not chemically bonded together. So this is why you do not keep the subscript. You turn it into a coefficient. B. Write the equilibrium expression. Pause to see if you can write this out. Products over reactants is equal to the K. The coefficient 2 turned into an exponent, and we have no solids listed, so there's no denominator. Now we need to find the molar solubility of the solution. Just like last problem, this is X from a rice table. This just gets slightly more complicated because there is a 2 coefficient on iodine. So let's write out a rice table. We don't care about the lead iodine because it is a solid and it is not plugged into the KSP expression. Initially, we have our lead iodide separate and away from the water. It hasn't been poured in yet, so we have 0 lead ions and 0 iodide ions. See if you can fill out the change row in terms of X. The lead ion is going to increase by some X term or variable, and iodine will increase by double that amount because for every lead iodide that you break apart, you're going to get 1 lead and 2 iodines. So here's the equilibrium values. This means that lead concentration is equal to X and iodine concentration is equal to 2X. Our equilibrium expression that we wrote from part B is this. So X is in place of lead, 2X is in place of iodine. Because of the expression that has an exponent, iodine is both doubled from the X and squared. This can simplify into 4X cubed. And now we need to solve this. The KSP is given in the problem. So we have 4x cubed is equal to 7.39 times 10 to the negative 9. Solving for the molar solubility is solving for x. Dust off your algebra brain and see if you can solve this. So this is the answer to the problem, 0.00123. Of course, you could put it in scientific notation if you wanted to. If the problem had asked for what was the equilibrium concentration of lead and iodine, then first you would solve for x, which would then also be equal to the lead concentration, but then double it to equal the iodine concentration, which would then provide you with these values. All right, let's do one last problem. Calculate the equilibrium concentration of all species in an equilibrium mixture that results from the decomposition of H2S with an initial concentration of 0.25 molarity. Here's the reaction, here's the K value. Pause to see if you can fill in the initial, change, and equilibrium values. Here's the initial. We only have 0.25 molarity of the reactant and 0 of each of the products. Fill in the change row. Coefficient of a 2 means minus 2x for the reactants. Coefficient of a 2 means plus 2x for the product and plus x for the other product that has a coefficient of a 1. Initial minus 2x is 0.25 minus 2x. 0 plus 2x equals 2x. Initial plus change equals equilibrium. So now that we have our equilibrium values here, this whole row, this is our goal row, we can plug them into our expression. We have products over reactants. Products are right here. Reactants are right here. These little exponents come from the coefficients. We have all of our values from the Rice table above. The H2 Rice table was 2x. The S2 value from the Rice table was x. And then the H2S had a value of 0.25 minus 2x. Pause to see if you can figure out what to do from here. Well, this would be an incredibly complicated problem if it wasn't for the fact that we can ignore the x in the denominator. And that means all of this right here. X is so small that even double x subtracted from 0.25 is still roughly equal to 0.25. And we know that x is small enough because this K value, it has a times 10 to the negative 9. So now it turns into this. Now pause to see if you can solve for x. So x should be 3.9 times 10 to the negative 4. The problem asked us for the equilibrium concentrations of each. So now go back to the Rice table and plug your value of x into each of these values.